Welcome to Mr. Frohlich's physics classes. Today we're going to see a general introduction to electrostatics. Hi there. Today we'll start our study of electricity. And the first thing we're going to do is just a very quick review of some of the concepts that are usually taught in maybe 8th grade or 9th grade, I don't know, but introduction to electricity. So let's first look at electric charge. So basically, the atom itself, the atom, is composed by a nucleus in the center, okay, and a cloud of electrons around it. So this region here is where we have a cloud of electrons. In the center, we have protons and neutrons, and in the cloud of electrons all around, we're going to have just electrons. As this first simulation from the gizmo from Explore Learning can show us, I think, if my memory does not fail me, this is a neon atom. So you guys can see the protons and neutrons in the center and the electrons orbiting around in a model that resembles more the planetary motion of for the electrons. Okay, so what we have is that the charge of the protons, okay, for the protons, we represent P plus for them. They're going to have a charge equals to +1 and a mass equals to 1. Okay, so we have protons in here. Now the neutrons, we're going to represent them by N0. They have a charge of 0, like their names say, and also a mass of 1. And then the electrons, which are moving around, these have a charge of -1 and a mass of roughly 0. Now, both of my picture about the atom and the gizmo simulation are actually extremely out of proportion. The nucleus is about 1/100th times smaller than the atom. So if I really think about the radius of the atom is about 100,000 times the radius of the nucleus. Okay? So this really means that this point here is tiny, 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 tiny. Now, for every, as a rule of thumb, for every proton, there is also a neutron. Okay, the number of protons and neutrons is roughly the same. Not exactly, but they grow together. And the mass of each proton is about 2,000 times the mass of each electron. So if I put the two ideas together, we see that the mass of the nucleus is basically 4,000 times the mass of the electron, the cloud of electrons around. So basically my atom is empty space. Okay, when you look at the atom, it's basically empty space. Yes?
Wow. I've never thought about that.
Oh yes, I agree. That is kind of impressive. Okay, and those electrons, especially the ones of the outer shell, they are not so strongly bound to the nucleus, and with some energy, it's not that hard to ionize them, to remove those electrons. And that's exactly all of our explanations that we're going to have in terms of electricity. Mary Jane?
Mr. Frohlich, can we ionize the atom by removing a proton from the nucleus?
Well, Mary Jane, technically speaking, yes, you can remove a nucleus, a proton from the nucleus. You can actually interfere, break a nucleus, but you need way more energy than what we're going to be discussing in here. Okay, that would need to be somehow nuclear reactions and other stuff. For us, in electromagnetism, everything that we're going to explain is going to be coming from moving electrons around. Okay? Our next step is to talk about fundamental charge. So the smallest charge that we can have in nature, that we can find outside of a particle, is the charge of 1 electron, okay? And therefore, we consider the electron to be the fundamental charge, and we're going to represent this charge of the electron as just being E. Now, Millikan, in an experiment that we're still going to discuss in the future, managed to measure this charge, and we have that in international units, this charge is 1.6 times 10 to the negative 19 coulomb, where a coulomb is the international unit of charge for Charles Augustin de Coulomb from Coulomb's law, the law of electric force between two charges. Okay? We will discuss more about this in the future, but basically this is the smallest charge that we can have around. And the charge of 1 electron is roughly the charge of 1 proton in terms of absolute value, which is 1 fundamental charge. Continuing our discussion, let's quickly talk about conductors and insulators. So, conductor. The characteristics of a conductor is that the electron of the outermost shell is not so strongly connected to the nucleus, as we can see on this simulation here, where the outermost electron is kind of shielded from the innermost shells of electrons from the interaction with the nucleus. If in here now we represent a piece of a conductor, piece of wire, so here's the wire, and these dots are representing the atoms of the grid of this wire, what we'll see is that that outmost electron that is not so strongly bound to the nucleus can easily actually be released, and it will be moving around inside of this space. So we'll have it moving around here, and then might bounce and might capture, and then moves back, and we just have those electrons moving around in random motion, not organized, just random motion back and forth, colliding with each other, colliding with atoms, and just moving around. Those electrons here, we're going to call them free electrons. And a conductor has a virtually unlimited number of free electrons. Okay? Examples of conductors that will be more important for us, I would say wires, okay, metals like copper, gold, silver, and the human body. Our body is also a good conductor of electricity. Now, insulator. Insulators are exactly the opposite situation of the conductor. The electrons of the outmost shell are strongly connected to their nucleus. You can still give some energy and pop them out, but you do not find in insulators free electrons moving around. So you can still take some electrons out, you can put some in, but you're not going to be able to conduct electric behavior from one end to the other in the domino effect like conductors will do. Typical examples that we need to know would be wood, rubber, glass, water. Okay, any questions? Yes, Mary Jane?
Mr. Frohlich, did you just say that water is an insulator? I always thought it was a conductor.
Yes, you see this. Water is an insulator. what conducts electricity are actually the salts, the ionic elements dissolved in water. Okay, so salty water will be a conductor, but distilled water is an insulator. Is this okay? So let's now talk about charging methods, the methods that I can actually charge an object. So the first example we're going to see is quickly charging by friction. Okay, so a very brief example of this is on the PHET simulation that I'm showing you right now here. But we have a fabric, let's say wool, and we also have a rod. The PHET simulation uses rubber balloons. I'm going to just assume here a rubber rod. And both are initially neutral. Notice that these two are actually insulators. So what I'm going to do is rub the rubber rod onto the wool. So I'm going to get the wool in here and rub the rubber on it. So get this here and just rub. And when I do this, I'm forcing the interaction between the atoms of the outmost layers of both materials, pushing energy into both. Now, one of those two materials is more likely to attract electrons than the other one. It's more electronegative. And then I'm going to have a net transfer of electrons to this one. On the PHET simulation, we have this net transfer of electrons from the wool to the rod or to the balloon. And then my step number 3, basically, is going to be to have the wool and then the rod and now that the rod has received electrons from the wool, it's going to have more electrons than protons, and therefore it's going to have a net negative charge. So it's going to be negatively charged. And the wool has lost electrons to the rubber, so it's going to have fewer electrons than protons, and therefore it's going to be positively charged. Notice that this charge will stay concentrated in the regions where they were touching, where they were rubbing. It does not spread all around because these are insulators. Any questions? Yes?
Mr. Frohlich, while I was preparing for today's class, I tried to rub two identical rubber rods but nothing happened. What did I do wrong?
Oh, I'm glad to actually see that you were preparing for the class. But let me try to give you some idea in here. If I rub two identical materials one another, both of them have the same probability or the same strength in attracting electrons. And therefore, I'm not going to have any net transfer of electrons from one to the other. So you're not going to be able to charge by friction two identical objects. Okay? Yes?
Mr. Frohlich, what if the rod was a conductor? Would we be able to charge the rod and the wool?
No. If you are using a conductor, that would not work this way. Because when you rub, if this here was a conductor, if I had in here a conductor, when you rubbed the conductor against the wool, this charge would have a tendency to spread all over it. Okay? And since you are then holding with your hand, so you have your hand or fingers wrapped around here, somehow, terrible hand I'm drawing, okay? But you have your fingers, that charge would also spread through your body. So no, this is a typical process that we're going to use with insulators. Okay? Any other question? All right. The next method of charging that we're going to discuss is charging by contact. And the first scenario I want to analyze is when I have two conductor spheres and the surface area of the first one is equal to the surface area of the second one. So let's consider here A and B. This is my scenario number one. And let's say that A is the same dimensions as B, identical metallic spheres. I'm going to first, somehow by any crazy method, push a charge I'm going to represent as negative 4Q on A. 4 chunks of charge. Now remember, the charge of each electron by itself is extremely, extremely small. Okay? So in a macroscopic world, when you just rub your hand, you already talk about gazillions of electrons. I'm just getting then 4 gazillions, 4 chunks of gazillions of electrons, and putting right here. Now, A is a conductor. So those electrons, this excessive charge, repels itself. They repel each other. And since A is a conductor, I have free electrons all the way around A. And those free electrons will then receive the repulsion of this excessive charge, and they will just bump their neighbors. And in a domino effect, they will actually spread around. It's not going to stay concentrated. Now, they will spread around, and this charge, this excessive charge, will actually end up spread over the surface of the conductor. Okay, and this process of spreading the charge around is extremely, extremely fast. If I remember right, about 10 to the negative 6 seconds for this here to happen. So for us, basically, if I have a conductor in static condition, the electric excessive charge is all going to be spread on the surface of the conductor. So I have here now my sphere A with a charge of negative 4, sphere B with a charge of 0, is initially neutral. So my total charge, initial, is negative 4Q. So in my step number 2, what I'm going to do is actually place these two in contact. When I place the two objects, the two spheres in contact, everything works as if I was giving the electrons a huge object, AB, for them to spread around. And what they're going to do, they'll repel each other, they will just spread all the way around. So now I'm going to have this charge this way. So in practice, I had electrons moving from A to B. This is what we really had. Now, my next step, step number 3, is to separate them. When I separate them, what I'm doing is getting this big AB and breaking down in half. And then A will end up with half of that charge, and B will end up with the other half of that charge. So my charge on A is negative 2Q, my charge on B is negative 2Q, my total charge final is still negative 4Q. You guys okay? In my next situation, let's consider now that B is twice as big in terms of surface area than A. So here is A on scenario number 1, and here is B twice as big as A. And I'm going to put a charge, this time positive, 6Q on A. The 6q will spread over the surface of A like this. Notice that plus 6q, putting a positive charge on A, actually means removing electrons from it. And as we did before, I'm going to put these two in contact. So, in the same way as happened before, when I put them in contact, what I'm doing is providing these positive charges, which is those lack of electrons, to significantly more space to spread. And what this guy's going to do is spread. So I'm going to have this positive charge now spreading around like this on the surface of this new big sphere. In practice, what I have in here is electrons moving from B to A. Okay? So it's going to partially neutralize A, and that process, B is going to become charged. And after this, I'm going to break them apart. But now I'm not breaking them in half and half, because B is twice as big as A. So I'm actually going to break them kind of here. So when I do this, my step number 3, I'm going to have A, B, and A now holds a charge 2q, and B holds a charge 4q. Notice that the charge total final is still plus 6q. Okay? So a couple things for us to consider. One, the total charge in any system remains constant. So Q total final equals Q total initial on an isolated system. This is known as principle of conservation of charge. Number 2, I don't like having rules of the outcome of any of these charging methods, because you change a little detail in how you do it and the outcome is going to be different. Reason it through, it's better. But notice here that in contact, the objects that I'm putting in contact, conductors, they will share the amount of charge, but they share in a way that's proportional to their sizes. So now here is the situation. What if one object was 20 times bigger than the other one? How their charges actually compare? After making contact, the 20 times larger object would take 20 times more charge. So the amount of charge remaining on the smaller one would be 1/20th of the other one. Yes, Mark, I have a question.
Mr. Frohlich, my dad told me that we need to ground the dryer so the electrostatic charge that would build up can flow to the ground. Is what you just explained related to what my dad said? What exactly is grounding?
Actually, that's exactly where I was going. Because when we ground an object, what we are doing is making electric contact between the earth and some tiny little object near the surface of the earth. And because of the proportional of the sizes, the huge size of the earth, what we have is that the amount of charge that remains on the object that I'm touching, the earth, is negligible. Is virtually speaking 0. So when an object is grounded, it's going to all of its excessive charge flows to the earth, and it should be discharged. But an object without the influence of any other charge, we're still going to discuss that. Okay? But that was a very good question. The last charging method that we're going to study is called charging by induction. And it is, for our purpose, for our interest, by far the most important one. In this discussion, as we're going to see, you'll learn several terms and several things that will be important for us. So please, bear with me and let's move forward. In my first step, I have the object I want to charge, let's say a sphere, and this object must be a conductor. Okay? And then what I'm going to do is get a charged object close to the conductor. Close, but not touch. So I'm going to bring in here my rod or charged object, whatever. And this one here is going to be called inductor. And it can be a conductor or an insulator. Let's say that this has a negative charge. So I just brought it in the presence of the other one. Now, what's going to happen is this here. The free electrons that I have in here will feel a repulsive force from the charge on the inductor and will push to the side, will move to the side. And as they move, they're going to push the next and the next and the next electron until I have an excess of charge in here. And when that happens, I'm now going to have on this end a lack of a negative charge, which means I have a positive charge. Now, I'm going to draw what I'm going to call now my step number 3 up here and keep building this process. So on step number 3, so I'm in this situation here. Now, let's say that I have another electron at some point in here, okay, electron of the material. This electron now is under the influence of two opposing forces. A strong repulsive force coming from the rod, plus a weaker force in the opposite direction coming from the internal charges, Fi. And if the external force from the rod is bigger than the internal force, I'm going to have a flow of electrons to the left, sorry, to the right, or to the far end. And when this happens, I'm going to have another negative accumulation on the far end and another lack of charge on the near end of the inductee. And with this happening, I'm going to increase this internal force. But while this internal force, while the net force on these charges is still not zero, they're going to be moving around. And I'm going to increase the separation of charge inside of my conductor. And again, that will increase the charge inside, the force inside. And this process will be happening until the net force on the system on those charges goes to zero. So charges rearrange until net force on each charge is zero. So charges rearrange until the net force on each charge is zero. So I'm going to represent this now here as a step 3.1, which is a repetition of that picture, just without all of this that we have in here. So my inductor, this, so notice that my sphere is still neutral, okay? This sphere is still neutral. What we did with the presence of the external charge is to induce electric poles. but it's still neutral. If at this point I remove my inductor, my external charge, these negatives will just move back and will neutralize the positives, and the whole thing comes back to this initial condition here. So after this separation, step number 4, still in the presence of the inductor, and then I have so step number 4 is still in the presence of the inductor. I will now make a connection between my sphere and the Earth. I'm going to make a ground connection, which is represented by this symbol here in electric circuits. And when this happens, I'm giving this excessive charge a way to run away, to flow further away from my inductor. And what they're going to do is just now flow towards the Earth. So this charge, now these electrons will move down towards the Earth, and I'm going to eliminate the charge on this side. So now my sphere has been charged by induction. Okay? But notice that if I remove the inductor while this object is still connected to the ground, those electrons will come back and the whole thing's going to be neutral. So before I actually remove the inductor, what I need to do is cut off the ground connection. When that happens, step number 5, I'm here, and now it's charged, and those electrons don't have any room. There's no room for charges to get in and out, no path. And so at this point, I'm going to remove my inductor, and then these charges will just spread around the surface of my sphere, and this sphere has been charged by induction. Let us go back to our induction process and see one more very interesting thing in here. So I have in here my conductor, my sphere, and I'm going to take the rod and bring it, and I'm going to take my charge rod and bring it close to the conductor. Let's say that this rod is now positive. Okay, so I'm just bringing this close to the conductor. And this positive charge will attract electrons to concentrate in one side, and then I'm going to have a lack of electrons on the opposite end. Now, notice this. Between this positive charge and the negative charge, there will be an attraction force. So I'm going to have in here a attraction force and a attraction force. And between the positive charge and the other positive charge, we're going to have a repulsive force. So I'm going to have here a repulsive force and here a repulsive force. But because the like charge is further out when compared to the opposite charge, the attractive force is always more intense than the repulsive force on this system. And then that means that when I put the two together, attractive force and repulsive force, what we end up getting is that the net force is attractive. So this is very interesting because what we have is that a charged object will attract a neutral object, or they will attract each other. So if you observe attraction, you cannot make the statement that the two objects have equal and opposite charges. You know for a fact that at least one of them is charged, and the other one is either charged with an opposite charge or neutral. To be sure that both are charged, I need to observe repulsion, because then I know that both are charged with equal charges, with like charges. Okay? Yes? If my object is an insulator, like paper, for example, inside of it, we do have molecules, and those molecules would have a nucleus, which is positive, and a cloud of electrons, which is negative. It could be a polar or non-polar molecule. Either way, in normal conditions, those charges, those poles, they are not oriented, they are just like this. And then my object does not show any special electric behavior. Now, when I get this object, this piece of paper, for example, and I approximate an external charge, as in positive, this external charge will attract the electrons, even the ones that are bound, and repel the nucleus. Well, the nucleus are not going to move, they're not going to change, but the electrons will somehow be slightly disturbed by this presence here, and they will start spending more time on one side of the nucleus than the other. And that will effectively create tiny little poles inside of my object. So what I want to have is molecular level electric poles. And they are kept in place by the presence of the external charge. This way. But when I have an alignment of those negative poles, most of them towards this side, and the alignment of the other poles on the other side, what I have on the big picture is now a negative electric pole on this side and a positive electric pole on the opposite side. So my insulator would also be polarized. It's going to show polarization, it's going to show electric behavior, and yes, it would be attracted. They would attract each other. That's exactly what happens with the tiny little piece of paper. Okay? And as usual, after watching a lecture, what we should do is now solve exercises to gain proficiency on the topic.